Now that we've added identity into the formal languages we're using, we have to add two final rules of inference to our proof system. Luckily, they're both pretty straightforward. The first, the identity introduction rule, just reflects the fact that everything is identical to itself. So this first rule says that at any point in a derivation, you can write down the width tau equals tau, where tau is any term from the language you're working with. So for example, if you're working with a QL identity language that contains the proper names M and N, then the identity introduction rule lets you write down M equals M or N equals N at any point in a derivation. And since the dummy names A, B, C, A prime, B prime, C prime, and so on and so forth are all terms of every QL identity language, the identity introduction rule also lets you write down at any point in your proof A equals A, or B equals B, or C equals C, and so on. Crucially, when you use the identity introduction rule to justify writing down an identity, the terms on either side of the identity sign have to be exactly the same. So this rule doesn't allow you to write down M equals N or A equals B. Sometimes you can derive a formula like that, but never just by an application of the identity introduction rule. This rule just allows the very boring M equals M or N equals N or A equals A and so on. The second rule, the identity elimination rule, is based on something that philosophers call Leibniz's law. Leibniz was a 17th century German philosopher / mathematician. And Leibniz's law says that if A and B are one and the same, then any property A has, B must also have, because A just is B. So to illustrate the identity elimination rule, which is based on Leibniz's law, imagine that we have some formula with a term appearing in it, like Fn, and there is an x such that ln x, which has the term n appear in it twice. That formula, like any formula with the name n in it, can be seen as attributing properties to whoever is named by n. So for example, if we suppose that n refers to Naveen, and we let f stand for the property of being funny, and we let L stand for the loves relation, then the formula at issue can be seen as attributing the property of being funny to Naveen, and as attributing to him the property of being such that he loves someone. Now, suppose we know that the individual named by N and the individual named by M are actually one and the same. Then, by Leibniz's law, we can conclude that the individual named by M also has the properties just attributed to the individual named by N. In other words, if we know that N equals M, then we should be able to conclude Fm, and there is an x, ln x, or Fn, and there is an x, lmx, or Fm, and there is an x, lmx. Any of those conclusions would be legitimate to draw because each is just taking a property or properties attributed to the individual named by N and saying, well, those properties must apply to the individual named by M too, assuming that N and M name the very same person. So the universal elimination rule allows us to draw any of those conclusions. In general, the universal elimination rule says that if you have a formula alpha with the term tau1 appearing in it, so putting tau1 in parentheses here after alpha just serves to indicate that the term tau1 appears one or more times within alpha. And you also have tau1 equals tau2 for some term tau2, then you can derive alpha, but with tau2 swapped in for tau1 in some or all of the places where tau1 originally appeared. So as another simple example, if you have for all y lya, and you have a equals b, then you can derive for all y lyb, swapping b in for a in the only spot where a occurs in the original formula. Or if you have fa and ga, and you have a equals c, then you can derive fc and ga, swapping c in for a in the first spot where a occurs in the original formula. Or you can derive fa and gc, swapping c in for a in the second spot where a occurs in the original formula. Or you can derive fc and gc, swapping c in for a in both spots where a occurs in the original formula. Suppose you have m equals m. Here you have a whiff with the term m appearing in it twice. And suppose you have m equals n. Then you can swap n in for m in some or all of the places where m appears in the first whiff. So you can derive n equals m by swapping n in just for the first occurrence of m, or you can derive m equals n by swapping n in just for the second occurrence of m, although you have the whiff m equals n already, so there wouldn't really be any point to this. Or you can derive n equals n by swapping n in for both occurrences of m, although there wouldn't really be any point to that either, since you could always get n equals n just by using the identity introduction rule. Now I should make one small modification to how I stated the identity elimination rule just a few moments ago. As I stated it, it says that if you have a formula with a term appearing in it, like fn, and you want to swap in another term for that one, for example, you want to swap m in for n to derive fm, then you need to have an identity where the term you want to swap out appears first, and the term you want to swap in appears second. So if you're starting with fn and you want to derive fm, then as I stated the identity elimination rule earlier, strictly speaking, you would need n equals m. The identity m equals n, where the term you want to swap out appears second, and the term you want to swap in appears first, wouldn't actually be good enough. So based on how I stated the identity elimination rule, if you had fn and m equals n, you couldn't immediately derive fm. You could still get from fn and m equals n to fm, but it would take a few extra steps. You would have to derive n equals m first. You would do that by using the identity introduction rule to get m equals m, and then you can see that formula as a whiff with the term m appearing in it twice. And since you have the identity m equals n, you can swap out m from the first spot where m occurs in m equals m and swap in n, which would give you n equals m. And now that you have n equals m, you can swap n out of fn and replace it with m to get fm. But it would be nice to avoid these extra steps, so we'll just modify our official statement of the identity elimination rule so that it says that if you have a formula with a term tau1 in it, and you want to swap out tau1 for another term tau2 in some or all of the places where tau1 appears in the original whiff, then the identity tau1 equals tau2 is good enough, where the term you want to swap out appears first, and the term you want to swap in appears second. But so is the identity tau2 equals tau1, where the term you want to swap in appears first, and the term you want to swap out appears second. Either one is fine. With that version of the identity elimination rule, we can go directly from Fn and m equals n to Fm.